Okay, hello everyone. Welcome to today's class. I am your trainer Maurice Monene. So in our today's class, we are going to discuss about a full crash course about the number systems, where we are going to go work on the operations and also do some calculations. So in a nutshell, let me give the introduction of what we expect in today's class. So in today's class, we expect that to discuss in details the four number systems that we have. So as we know from the slide that I have displayed, all data in the modern computers is stored as a series of bits, a bit being a binary digit. And remember, a binary will always take the two states, that is either a 1 or a 0. The most basic form of representing a computer data is to represent a piece of data as a string of ones and zeros on each case of the bit. And this is simply what we call the binary or base 2 numbers. And we said the base 2 numbers or the subscript of 2. And because binary notation requires so many bits to represent relatively small numbers, two further compact notations often used are either octa or decimal, and we said this one we are going to discuss them in details. And most computer programmers who design sequence of numbers code including a computer codes instructing a computer what to do would have very difficult task if they were forced to work with nothing but long strings of ones and zeros, the native language of any digital circuit. Octa notation will represent data as base 8 numbers with each digit in octa number representing 3 bits. And similarly, hexa notation uses the base 16 and representing 4 bits with each digit. Then we have octa numbers using only the digit 0 to 7, while hexadecimal numbers all uses base 10 and A to F representing that is A to F representing 10 to 15. So let us start with the binary, and we say that for the binary here we have the system numbers in everyday uses the denary or the decimal system numbers using the digit 0 to 9, which has 10 digits, that is 1 0 1 2 3 4 5 6 7 8 and 9. And this one we say that their radix are all base of 10. The binary system of numbers has a radix of 2 all. That is the only take 0 and 1. Conversion of the binary to decimal. So for instance, if we take the decimal number 2, that 4.5, this one is equivalent to what? Let us get the total values, and for us to get the total value, remember we multiply the digit multiplied by its place order or place value. So for instance, if I take 5, the place value of 5 is a tenth, and a tenth means 1 out of 10, and 1 out of 10 in indices, we can write it as 10 raised to power negative 1, 10 raised to power negative 5. So the total value of 5 will be 5 I multiply by 1 out of 10, which is 0.5. The same place, the place value of 4 is 1, and the total value of 4 becomes 4 multiplied by 10 raised to power 0. And you know that any number raised to power 0, any number raised to power 10 raised to power 0 will always be 1, and this gives us the place value of 1s. Then 3, the place value is tens, and tenth is the same as 10 raised to power 1, and the place value of 2 is 100. 100 is the same as 2 squared, or 2 raised to power 2, which gives us a 10. So now if we take 2 times 10 raised to power 2 plus 3 times 10 raised to power 1 plus 10 times 4 times 10 raised to power 0 plus 5 times 10 raised to power negative 1, we can be able to get the sum of the terms comprising in these. So that's simply what we can say. The sum of the terms comprising or a digit is multiplied by the base raised to the power form. So the same case in the binary system numbers, we take the base 2, so the base now becomes the 2. So now what we get, the place value of 1, the first one, it is 1, then we multiply by 2 times 2 raised to power negative 1, 2 raised to power negative 1, 2 raised to power negative 1. Then the second one, the second place of 1, it is 2 raised to power 0, 2 raised to power 0. Then we have 0 plus that. So if we sum up these, we get the decimal number equivalent to the binary number 1 is the same as that. Is the same as the first one. If we work out, we get 1 times 2 raised to power 3. That one is 8. That one is 8. And then we also have 1 times 2 raised to power 2. That is 4. And then we have 0 multiplied by 2 raised to power 1. Any number multiplied by 0 is a 0. And then we also have times 1 times 2 raised to power 0. 1 times 2 raised to power 0 is not a 0, because 2 raised to power 0 is 1. So 1 times 1 becomes a 1. And then we have plus 1 times 2 raised to power negative 1 is the same as 1 multiplied by a half. 1 multiplied by a half. So that one becomes 0.5, or simply what we have as 0.5. So if we add them, we get now 1101.31 is equivalent to 13.51 base 10, 13.5 base 10, sorry, 13 times 10 base 10. And this one takes the surfaces of 2 and 10, denoting binary and decimal, denoting binary and decimal. Problem 1, or example, if we want to convert 1011 base 2, this is base 2, to a decimal number from the above, we take the digit, multiply it by equivalent place value. So the first one, we are going to have 1 times 2 raised to power 4, because here we have, this one is ones, tens, hundred, thousands, and tens of thousand. In tens of thousand, this one is equivalent to 10,000. So we have, but here in this case, our base is not 10, it is going to be 2. So the first one is 1 multiplied by 2 raised to power 4, and 2 raised to power 4 is 16. 2 raised to 1 times 2 raised to power 4. So this one takes the first value here, and then the second value becomes 1 times 2 raised to power 3, then plus the other one becomes 0 times 2 raised to power 2, and then we have plus the other one becomes 1 times 2 raised to power 1, and then the other one becomes 1 times 2 raised to power 0. And remember, we said that any number raised to power 0 will give us 1. So in this case here, we get 1 times 1, which is a 1, and here we get 1 times 2 raised to power 1. 2 raised to power 1 is the same as 2, so this one gives us a 2. And then this one gives us a 0 multiplied by any number will always give us a 0. And here 2 times 2 raised to power 3, this one is a 8. And here this one is a 16. And if we had the 16 plus 8 plus 0 plus 2 plus 1, we get a 27 suffix of 10. In the problem 2, this one we can convert it still. You remember, when we get to a point, from a point moving away towards the light, we get a tenth, hundredth, a thousandth, a tenth of thousand. So in this a tenth of thousand, so in this case now we are going to have 1 times 2 raised to power negative 1, which is the same as a tenth. So to get the sum of the values in equivalent of the decimal number, then the other one will be 0 plus 0 times 2 raised to power 0 plus 2 raised to power that. So in this case here we are going to have this one being what? This one being half, which is equivalent to 0.5. Remember we said that 2 raised to power negative 1 is the same as 1 all over 2 raised to power 1, to do away with the negative in the power. So the second case will be 0 multiplied by 2. So here we are going to have half. Any more number multiplied by 0 becomes a 0. Then plus the other one is plus 0. Then plus this one is the same as 1 out of 8. 1 out of 8. Then plus the other one becomes 1 out of 2 raised to power 4, which is 1 out of 16. So equivalent decimal numbers, this one is the same as 0.5 plus the other one is 0.125, then plus 0.0625, and when you add these you get into base 10, you get 0.6875 base of 10. So that is how we convert the fraction bit. That's how we convert the fraction bit. So in our other example that contains both the fractions and the decimal part and the whole part, remember in this case we have two parts. The first one, we have this one is ones, hundred, tens, then hundreds. So the power of this becomes 2 raised to power 0, because it is ones, and this one becomes 2 raised to power 1, then 2 raised to power 2, and then the difference here, 0 becomes 2 raised to power negative 1, then the other one becomes, this takes 2 raised to power negative 2, then this takes 2 raised to power negative 3, and then this one takes 2 raised to power negative 4. So in this case we are going to have the first one, which is 1 times 2 raised to power 2 plus 0 times 2. So 1 times 2 raised to power 2, then plus 0 times 2 raised to power 1, then plus 1 times 2 raised to power 0. So when you add these, you get a 4. You get a 4 here. Then 0 multiplied by any number, we said this one is a 0. Then plus 1 times 2 raised to power 0. Remember we said that any number raised to power 0 is a 1. So 1 times 1 becomes a 1. Then 0 multiplied by any number becomes a 0. Then plus 2 raised to power, this one is the same as 1 times 1 out of 2 raised to power 2. So this one is the same as 1 out of 4. Then plus the other one, this one becomes 0. Any number raised to power 0, any number multiplied by 0 is 0. Then plus the other one, this one is the same as 1 times 1 out of 2 raised to power 4, 2 raised to power 4, which is the same as 1 out of 16. And when we convert them to the equivalent decimals, this is how you get, and then you get the answer as 5.325. So we can also have the conversion of decimal to binary. Conversion of the decimal to binary, and an integer decimal number can be converted to a corresponding binary number by repeatedly dividing by 2, noting the remainder at each stage. as in the case of the example that we have here, the result of that. And remember this technique, we normally call it successive division techniques. Successive division technique. So let us work through that 9 and we convert it to binary. So remember the first thing, we defined that 9 divided by 2, we get what? A 19. Then the remainder here is what? The remainder is 1, because we get the remainder is 1 because we get 19.5. We take 0.5, which forms our part of the remainder, then we multiply by 2, we get 1. We get 1 as our remainder. Then again we divide 19 by 2, we get a 9, which is 9.5. So if you take 0.5 bit, you multiply by 2, you get a remainder of 1 also. You get a remainder of 1. And then from there, if you take 9 again, you divide by 2, you get a 4 with a remainder of 1 again. And if you divide by 2, you get still a 2 with a remainder of 0. If you divide by 2, you get 1 with a remainder of 0. And then if you divide by 2, 2 divided by 1, of course it is more than, you get a 0 with a remainder of 1. And in this case, remember we said that the most significant bit is the one we have got last here. The last remainder is the most significant bit. Then moving upward to the first one, which was the least significant bit. So to record our answer now, we record from starting from the most significant bit to the least significant bit. So our answer becomes 1 0 0 1 1 1. Remember always to include the subscript or the bits to separate the different number systems too. So and that becomes the equivalent binary of 39 base 10. 39. So if we convert the 0.40625 to binary, this one we don't divide when converting the fractions or the decimal, but what we do, we repeatedly multiply by 2 until we get 1.00. So in our case here, we are going to first of all have 0.40625. Then we multiply it by 2. If you multiply by 2, you get 0.0.81225. 0.125. So remember here, if we are recording our answer into binary, it is a 0 point because the other bit is 0. And now our most significant figure, most significant bit or digit is 0 here. So we record that first 0 there. Then again we take 0.8125, we multiply by 2, and in this case we get 1.625. We take our part, which is 1, and then we multiply again by 0.625 by 2, we get 1.25. We take our bit, which is all part 1, and then we multiply again by that is 0.25. we multiplied by 2. In this case we get a 0.5. so we record our 0 here, and our least significant figure bit now, we multiply 0.5 by 2, we get 1.0. So you can see now there is nothing left for us to multiply with, because 0 multiplied by 2 will always give us a 0, so we can record the 1. So now our equivalent conversion of 0.0625 base of 10 is equivalent to 0.01101 base 2. So that is how we convert the fraction. So only the difference is in the most significant bit in this case and the least significant bit and like where we were dividing with the twos, and then we have something else we call the binary operations, and in this case we are going to measure ourselves with two. We can do the binary addition and the binary subtraction. So to start with the binary addition, you need to understand the basic rules of addition. So whereby we have a 0 added to a 0 will always give you a 0, and also if we have 1, we want to add it to 1, this one will give you a 0, but now with a carry over here, which is 1. And if you can convert this one to the binary that is the decimal representation, a 1 added to a 1 will always give you a 2, and this one is always a 2. And also you need also to put in your mind that when we have 1 added to 1 and another one, that is 3 successive ones, this one will always give you a 1, but this one now also will have a change, a carry over of another one, and this one a carry over of 1. So now let us have our first example here, which we have 1 0 1 0. We add it to 1 0 0 1. So if you had remembering the basic rules, 0 added to 1, this one will always give you a 1, and then 1 added to 0 will always give you a 1, and then 0 added to 0 will always give you a 0, and then 1 added to 1 will give you a 0, but now with a carry over of 1. If you can convert let us convert this one to their equivalent. We convert them to their equivalent binaries by dividing them into different columns. Let us divide them into different columns. So remember, this one is a 2 raised to is a 1 because of 2 raised to power 0. That is the place values. If we take the second one, this one is a 2. If we take the other column, this one is a 4 because of 2 raised to power 2. This one, it is a 8, and also this one is a 16. So let us see the place value of this. So here we have 2, and here we have 8. So if you add 8 plus 2, you get the binary equivalent of this was 10. And here we have a 1, here we have a 8. If you add 1 and 8, you get a binary equivalent, decimal equivalent of that. So if you add 10 and 9, you get a 19. So let us see if the result was equivalent to this 19. So remember, here we have 1 plus 2, then plus 16. 1 plus 2 plus 1 gives us 19. Very true. So we can also have the other state. Here we have 1, that is 1 0 1 1 0, and this one added to 1 1 0 1 1. If you had the same, you are just going to get the same value comparing to what we have added. You can pause and try the other two. You see if you are getting the same value, and then you can use the 12486 code to confirm your answers if it is correct to the equivalent. Then when subtracting, you need also to have the basic rules, which state that 1 raised to power 1 minus 0 is equals to 1, and 1 minus 1 is equals to 1. So we can have the first one, which is 1 0 1 0, sorry, I don't know how my 0 have drawn it. Then we subtract 1. If you subtract 0, of course you cannot, it is impossible to subtract 1 from a 0, so we need to borrow 1 here, and if we borrow 1 here, we cancel out this one, we leave 0 there, and then we have 2 here. And then if you take 2 minus 1 becomes a 1, so you can decide to bring this 0 here. Let us convert them. This one is a 1, this one is a 2, so meaning that this one, the binary equivalent, the decimal equivalent was 2, and this one was 1, and if you subtract you get 1, so you can see it is correct. So the same case you can take the other one, which is 1 0 0, then we subtract 1 and a 0. If you subtract these two, you get also 0 minus 0 is 0. If you have 0 minus 1, remember it is impossible this, so you borrow 1 from here, this one cancels to leave 1 0, and this 2, so it becomes 1, and decided to drop this other 0 here. So if you convert this to the binary, this one is a 4 minus 2, not wrong, which is a 2, and this one I think it is a correct. 1 0 is equivalent to 2 in the binary representation. Still you can have 0 1 0 0, you subtract 1. Remember here it is not possible to subtract, and you cannot borrow from 0, so you borrow from here. If you borrow from here, you leave a 0, and here it comes as a 2. If you borrow here, this one leaves 1, and here it comes as a 2, so 2 minus 1 becomes a 1, and then here we add 1. You can decide to bring this to 0 here, and that is how, if you convert this one to, of course, to the decimal representation, it will be a 3, and this one is a 2, this one is a 4, then 4 minus 1, of course, is a 3. So you can do as many examples to you to be perfect, as many as example you look them from different. We have a number like what has happened with my highlighter? So we have a number like 4 3 1 7. So if we divide it by 8, here, the first 8, remember how we have recorded the decimal part, we get a 61, then remainder 5. Then if you divide 8 again by 61, we get a 7 because of 56, remainder 5 also. And if we divide 8, we get a 0, then we remainder 7. So remember our most significant digit is 7. Then moving upward, this one becomes our least significant digit. So in this case, our answer becomes 7 5 5 base of 10. So this one base of 8, sorry, base of 8, not base of 10, base of 8. So this one is equivalent to it is equivalent to 493, sorry, this one was 493, that one was equivalent to 493, not into the base of 10. Also we have the hexa numbers, and we say that the hexadecimal system is particularly important in computer programming, since for bits each consisting of 1 or 0 can be expressed using a single hexadecimal digit. 2 hexadecimal digits represent numbers from 0 to 255, a common range used, for example, to specify colors. That's in the HTML, that is the hypertext markup language of the web. Colors are specified using 3 pairs of hexadecimal digits, that is RR, GG, and BB, which represent the red, green, and blue. And remember, this one is the primary colors. So we take that the hexa number system has a radix of 16, and it uses the following, that is 16 distinct digits. 0 to 9, then A, B, C, D, E, F, where A takes 10, B takes 11, C takes 12, D takes 13, E takes 14, and F takes 15. A takes 15. Still, if we have the converting from hexadecimal to decimal, you multiply the digit with its place value. So like in our case here, we have A1A base 16, which is the same as A multiplied by 16 raised to power 0 plus 1 times 16 raised to power 1. A is equivalent to 10. Then multiply by any number raised to power 0 is 1, then plus the other one is 1 plus also 16 times 16. So in this case we get 10 then more added to 16, and which is giving us a 26 base of 10 is equivalent to 1A6. And similarly we have the other ones, which is maybe for instance a 2E. Also we can use the same knowledge. 2E16. So the first one, remember E, we are going to multiply it with the place value of 1, which is E times 16 raised to power 0. And remember in our case E is a 14. E is our 14, and then 2 times that, so becomes 32 added to 14, which gives us a 46 base of 10. 46 base of 10. The same case with 1BF. So we get 1 times 16 raised to power 2, 16 raised to power 2, then plus B times 16 raised to power 1, then added to F times 16 raised to power 0. And remember here in this case, this one 16 squared is a 256, then plus B is equivalent to 11, so 11 times 16 becomes 176, and then F is equivalent to 15 times 1, which is equivalent to 15. If you add, you get 447 base of 10. So to convert from decimal to hexa, you repeatedly divide by 16. So for instance, we have a number like 26, the one that we have already done. We divide it by 16. How many times does 16 go to 26? It is just 1. Then with a remainder of 10, and then how many times does 1 go to a 16? This one is a 0 time, but with a remainder of 1. So if I was to reckon this one, remember 1 here becomes the most significant digit, and moving upward this one becomes the least significant digit. So if I was to reckon, this one will be 1 and 10, and remember this 10 is more than 9, so I'll use the equivalent letter. So I'll have 1. 10 is equivalent to A base of 16. The same case we can have the same another which we had here, which was 447. We can also divide it by 16. If you divide 447 by 16, you get a 27 remainder 15. Then you divide again by 16, you get of course 1 remainder 11, and if you divide by 16 again, you get a 0 remainder 1. So if you are to reckon, your answers will be the most significant digit will be here down, so it will be 1, 11, then 15. And remember this one, they have equivalent representation, because if you write them like this, they will be read otherwise. So it will be 1, then B, and then B for 11, and then F for 15 base of 16. Always remember to include the bases. So then we have converting from binary to hexadecimal, and for conversion of these, we say that the binary bits are arranged in a groups of 4 starting from right to left, and an hexadecimal symbol is assigned to each group. For example, the binary number, there is a big number that is there, that is 11100111, is initially grouped in 4, and when we group in 4, for example, we have the first group 4. If you can convert that is 1110. Let us convert it to binary, to the decimal equivalent. So this one is 0 times 2 raised to power 0, then plus 1 times 2 raised to power 1, plus the other one is 1 times 2 raised to power 2, then plus the other one is 1 times 2 raised to power 3. So times 2 raised to power 3 times 2 raised to power 3. So 0 times 2, this one is 1, then plus 2 plus 4, then plus 8. So this one gives us what? This one gives us 3, 7, 3, that is 3, that is what? This one gives us 3, 7, 7, that 15. It gives us a 15. So if you convert this one is a 10, this one I think it's a 14. Sorry, is it 14? 14 or 15, supposed to be F. And the hexadecimal of this. So if you group them in 4s and then you convert them to the equivalent the decimal, the way you have converted, you get this. So also we can convert by grouping. So let us convert the other one. Which is 1101. We see. So this one is 1 times 2 raised to power 3, because this one is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, then plus 1 times 2 raised to power 2, then plus 0 times 2 raised to power 1, then plus 1 times 2 raised to power 0. So the first one, this one is 1 times 2 raised to power 0. Number raised to power 0 is 1, then plus 0, then this one is plus 1 times 2 raised to power 2, that one is 4, then plus this one is 8. If you add these, you get something to do with 13, and from the binary representation, 13 is the same as D. Good. So that's why we have the D there. If you convert the other one, you get a 6. So that is how we do by grouping the 4, and then we can be able to get the decimal equivalent of 16 by grouping. Also, we can do the converting from hexadecimal to binary. There is no the one that we have done here, but the best way that you can do for this, so that you can see if it is true, remember this one. First of all, we can convert it to via the decimal. That is, we have 3 3 times 3 raised to power, this one is 16 raised to power 0, 16 raised to power 1, 16 raised to power 2, 16 raised to power 3. So we have the first one, which is 6 times 16 raised to power 3, then plus c times 16 raised to power 2, then plus f times 16 raised to power 1, then times the other one is 3 raised to power 3 times 16 raised to power 0. And then remember to include the binary, the number for c, that is I think 12, f is 15, and then you can multiply to this, convert the way we have converted it to a decimal. Then from the decimal, now you can be able to convert it to binary by successively using the successive techniques of dividing by 20. take a pause, do that, and then you can post your answer in our chat so that we can see how you did, and then we can do it in our next class. And that brings to the end of our session. If you have found it helpful, consider subscribing to this channel for more videos like this. Like it, share to reach more students so that they can also benefit. Thank you. I am your trainer, Maurice Monene.